Okay, as we start Chapter 2, Topic 1, Chapter 2 deals a lot with function, and we're going to give you a quick example, then we're going to go into the meaning of function in much more detail. I've covered this on a lot of other videos that I've produced, but let's follow what's in our textbook. Here on page 44, Example 1, they're talking about point-by-point plotting. And what does that mean? Well, initially you make a T-chart, X and Y, and then you're going to put various values in for, let's say, the X. And we're dealing with this particular quadratic now because of X to the second power equation. And we say if X is a negative 4, we're going to square a negative 4, get a negative 16, a positive 16. Then we apply the negative sign. That's a negative 16. And then plus 9. So a negative 16 plus 9 gives us a negative 7. And then if this is a negative 3 squared is a positive 9, then we apply the negative sign. So 9 minus 9 gives us a 0, and we get these various values. So this is just basically arithmetic and substitution. Now you have to keep in mind, you need to get the right signs and the right numbers. But now let's just practice plotting it. So there's a negative 4 and a negative 7. So we go here to negative 4. 1, 2, 3, 4. There's negative 4. Then we go down 7. 1, 2, 3, 4, 5, 6, 7. So we have a point about there. Then we have 3, 0. 3, 0 is right there. Negative 2, 5. 1, 2, 3, 4, 5. Right about there. Negative 1, 8. 1, 2, 3, 4, 5, 6, 7, 8. 0, 9. Then 1, 8. 2, 5. I don't know if you're seeing a pattern here. 3, 0. And 4, negative 7. So there are our plots. And now we are directed to carefully connect these points in a smooth curve. So let's see what I can do here. There we go. And that is the point-by-point plotting of this particular graph. And when you're doing this on MathLab, they often will give you graphs that have been done. You have to sort of match up what you're getting from your T-chart as to what they're illustrating as a graph. Now in a corresponding example where they give you this one right here, y equals a negative x to the third plus 3x. And if you were to make a little T-chart using the points negative 1, 0, and a positive 1, you would actually get these 3 points. And if you plotted these 3 points, it would look like so. And you might think you have a nice linear equation. But here's a case where you plotted actually too few points, because the next one would have gone up like so, and this comes down like so. So this particular graph looks like this. And in fact, to check it, and again, we don't use calculators in class, but hopefully you can see sort of what's going on there. The key to what we're illustrating here is that if you have too few points, sometimes you don't get the nature of what the graph would look like. Okay, that would be example 1 on page 44. It extends to page 45. Okay, now we're continuing, and we're going to what is called define a function. Now, depending on what previous courses you've had, you may know some of this, but I think we'll do some basic review on what is a function. Well, first of all, you know what this is. This is an ordered pair. And we know this can be plotted on a graph, and that the x and the y are in a sense related to each other, and they have that connection. Well, the ordered pair is a good example of what a relation is. This is a mathematical relation. Now, within this relation, this ordered pair, we have what is called a domain. By definition, the domain refer to the x elements in an ordered pair. And the range refer to the y elements in an ordered pair. And to finish our definitions here, something is a function if the x element is only used once in a particular series of x terms. Now, in the textbook, they give you 3 tables that I'm not going to draw, but we see from the domain, which would be our x elements, there is a straight line going to the range. In table 2, again, a straight line going to a range. But in table 3, from, let's say, number 1, there are 2 lines. So that indicates that the x element, the 1 there, is used more than once. So if the x element is only used once, it's a function, as we see in table 1 and 2. While in table 3, the x element is used more than once. And we'll give you some more examples of that as we go on. Now, we're jumping ahead just a little bit because I think this would be useful. In fact, before we jump ahead, though, let me make a graph or a little diagram. These would be your x elements. These are your y elements. And let's say we have A, B, C, D here. X, Y, Z, and S. I ran out of letters. And if we had something like this, again, the x element with 1 line from it indicates it's only used once. We had that same thing, A, B, C, D, W, X, Y, Z. Here, this would go there, this would go there, this would go there, this would go there, and that would go there. And you'll notice from the A element, which is an x, there are 2 lines. So this is not a function, while this is a function. Again, the x element only used once. So that's sort of a shortened tool. It's a little more complex than that, but we like to use that. And then another tool, if we have a graph of something, and if it's in the form that I have illustrated here, we have what is called, and I believe this is on page 48, what is called the vertical line test. And what it is you have a vertical line that's very thin, that you're going to move this vertical line over the face of the graph. Now, as this red line goes over the face of the graph, does it intersect the graph that you've drawn in more than one place as it moves over the face of the graph? And for this one, no, it only intersects in one place. So this is a function. Now, remember, this is positive slope. So any linear equation that has positive slope is a function. This is negative slope. And again, does it pass the vertical line test? That it intersects only in one place as you move it over the face of the graph? And the answer is yes. So this is a function. Any positive or negative slope, linear slope, is a function. Now, how about the horizontal line? You recall this equation is y equals 3. Does this pass the vertical line test? And the answer is yes. So, zero slope examples are functions. Now, this equation, you might recall, was x equals -2. It's a vertical line. Does the vertical line test, when you put the vertical line over a vertical line, does it pass the vertical line test? That is, does it intersect at only one spot? No, it intersects at an infinite number of spots. So this is not a function. How about an upward opening parabola? Does this pass the vertical line test? Well, as you notice, the answer is yes. So this is a function. And by the way, if the parabola opened to the bottom, that would pass as well. Now, how about a parabola that's to the side? And in this case, we have something that's y squared. If y squared is in that little formula, it's going to be a parabola sort of opening to the side. Does this pass the vertical line test? No, because over here it's intersecting in two places. So this is not a function. And this is an example they give us in our textbook. Does this pass the vertical line test? Well, no, it's intersecting there and intersecting there. So this is not a function. Okay? In example 3, they're asking us to find the domain of our, in this case, the x values. That would be our domain item. And I've put in a few little extra things from other courses where this would be a typical positive slope. What would be the domain? And again, domain are our x values. So where is this line coming from? Well, it's coming from over here, negative infinity. And where is it going to up this way? Positive infinity. So to put it in interval notation that we introduced in chapter 1, and for infinities, we always use a parenthesis. And the domain then of our x values for this line would be from negative infinity to positive infinity. And if you wanted to graph that, it would be a graph in which everything is filled in. And it goes on to negative infinity this way, positive infinity. Now, for something like this, where you are specific, what we do here is we drop down and drop up, in a sense, these values. So what are they? 1, 2, 3, 4, let's say. 1, 2, 3. So the domain then of these x values for this line segment, it would start at, and since that number is included, is a -4, starts at a -4 and continues up to a +3. And again, we use brackets to indicate that those numbers are in our set. That's interval notation. And the actual example they give you for example 3 is this. It's the square root of 4 minus x. Now, whenever you have a radical sign, the smallest number you can have under the radical sign and have it be a real number is 0. Because lower than 0, you start to get negative numbers under the radical sign. And those are imaginary numbers, they're not real numbers. So, how do you solve that? Well, you take the radicand, which is the part under the radical sign, and equate it to 0. You're saying that this radicand has to be greater or equal to 0. Now I'm going to just transpose my x to the other side. It now says x is less than or equal to 4. Now, how do I graph that? Well, again, for some of you may want to write it this way. X is less than or equal to 4. So there's the number we're interested in, the 4. And it's x is less than or equal. So for that, we use a bracket at 4, indicating that 4 is in the set. And then we put a line this way. Now, what does this mean? Well, these numbers now are coming from -infinity up to and including a 4. And that is our interval notation for the domain of this function. Now you might say, how come these are negative? And the reason is because x is x, but then we're saying minus x. So as long as x as a number that's 4 or less than 4, this continues to be positive. But as x is negative itself, not it would be minus a negative, whatever value, that makes it a positive. That's why we have these negative values here. Because the opposite of whatever negative value x is will make it positive. All right, we're continuing on with, again, some review items, but important basic concepts in function notation. Well, the general item of function notation is this symbol right here. Now, these parentheses do not indicate multiplication, but are part of the function notation. In some cases, another letter might be used instead of F for gravity or for height. But this would be the symbol of function notation, and it would be read as the function of x is such that 2x plus 3. Now you might say, this looks very familiar to this. That is slope-intercept form. And the answer is yes. But instead of a y, we use the function notation. And that leads to something that often you can substitute the y for the function notation. But it's something you should become acquainted with and use. So, for instance, if they are asking you to do some examples in which they want you to solve, for instance, f of 2. So 2 is your x term. So in a t-chart, you might set it up like so. Then they'll want the value of f where x is 1 and where x is 0. So this is a good little tool, the use of the t-chart when you're working with function. You'll see a more complex example in a minute. So what is that? Well, if x is a 2, 2 times 2 is 4, 4 plus 3 is 7. If x is a 1, 2 times 1 is 2 plus 3 is 5. If x is a 0, 2 times 0 is 0, this becomes 3. So you would say then, when f of x, where x is 2, the function, the y value, is 7. This is your end result. And we often run into a situation, looks something like this. We talk about input, and then we have output. And what we're putting into this particular function is the value of 2. So as we put 2 into our function, and that would be 2x plus 3, the input of 2 into that will give you the output of 7. And another thing we tend to say is an independent variable and a dependent variable. Our independent variable is 2, and our dependent variable is 7. So when we put 2 in there as an independent item, it comes out as a dependent item on that 2. Okay, that's some background on function notation. Now we'll get to a specific example. Okay, now we've moved into some examples where they're saying, this is example 4, they're giving us 3 functions. In this case, it's a function of x, a function of g, a function of h. And they're defining what that function is. Here it's going to be 12 divided by x minus 2. Here it's 1 minus x squared. And there is the square root of x minus 1. Now in the example, they give you, we'll say a, the function of x, where they're giving you this value of x as a 6. So I put the 6 there. Here they're going to give you a value of g, where they're saying this x is a negative 2. And here, this x is a negative 2. We'll get to this other one later. So what do? Well, we take the 6, put it in there. 6 minus 2 is 4. 12 divided by 4 is 3. And again, I'm using the t-chart to help me organize my data and see the relationship of these things. All right, here we have a value for g of a negative 2. So wherever there's an x, we put a negative 2 there. Now a negative 2 squared is a positive 4. Then we apply the negative sign, so that's a negative 4 plus 1 gives me my negative 3. And then here we have a negative 2 and a negative 1 gives me the square root of negative 3. Now I don't know if you recall, but this is not a real number. But they're not asking that here. Okay, then they gave us number or letter D, where they're saying the function of this, where x is 0, g, the x is a 1, and here h is a 10, and they're giving us a sequence of how we apply this, where we're going to find this, if this is 0. So I put my x value as 0. If this is 0, I have 12 divided by -2 gives me a -6. So this is going to be a -6. Now, if I put a 1 here, if I square 1, I get 1. 1 minus 1 is 0. And then if I put a 10 there for x, 10 minus 1 is 9. And the square root of 9 is 3. So I'll put a -3 there, because it says negative. So now I add these up, and I end up with a -9 as the answer to letter D. Again, all this work is in the book. We're just trying to give you a little insight into it. Going over it may be a little help. Example 5 is a continuation of example 4, but they want us to find the domains of the x term. Now, whenever x appears in the denominator, remember what value would make this denominator a 0? Well, we use that technique, x minus 2 equals 0, x equals 2. So if x were a 2, x minus 2 would be a 0. That is, 2 minus 2 is a 0. So we say when we are defining our domain for a variable in the denominator, it cannot be a 2. So in setting it up, depending on what method you're using, in interval notation, in this case, we could use both actually. Set builder notation. X is such that x is a real number, but x cannot be 2. Now in graphing that, it would be a solid line. Looks like we're having a little thunder there. Where we have 2, right there, and there would be a hollow on 2, but it would be all the other numbers. And in interval notation, this would be from -infinity up to 2, but not including 2, and then in union with 2, but again not including 2, up to positive infinity. That would be the domain of this particular example. Now, when we don't have variables in the denominator and it's not in a radical form, our domain is all real numbers. And we usually just use the capital R, or from -infinity to positive infinity. And in this one, again, we're looking to have that radicand. And we say x is equal to, actually x is greater than or equal to 1. So in this case, similar to the previous one, we equated it to 0, but it has to be greater than 0, so that x is greater or equal to 1. So on a graph, it would be a 1 there, bracket, and like so. Interval notation, it would start at 1, going up to positive infinity. Now again, our x is positive, so we don't have what we had in that other example. Now in this next example, it's rather daunting. Again, we're dealing with function notation. Page 51 for details. Example 6. The function of x is x squared minus 2x plus 7. And now what they want you to do is to use this function, and they're giving you various values of x to put into that function and see what your output would be. So in the first case, they're saying let x be a. So all we do is take the a, and whenever there's an x, we put the a there. That's pretty straightforward. Now in this next case, they're saying the x is a plus h. This is what x is. So to elaborate, we have to take our x, put this value where the x is, which is what I've done here. So this is x, and we're squaring it. Then it's a negative 2 times what our x value is again, and then the plus 7. Now this isn't finished. I left it that way purposefully so you could see what needs to be done. We now have to take, and I guess I can do it over here, a plus h and square it. Now in my algebra class I taught a method for squaring a binomial, and I'll review that with you right here. But first let's use the old-fashioned method of FOIL. And we're going to FOIL these, and that gives us a squared. We're going to do our outers. That gives us a positive AH. Our inners, another positive AH. And our last, which gives us h squared. Now we see we have like terms in the middle. There's two of these, so we can get then a squared plus 2ah plus h squared. So this is what this becomes when we square it. Now we have to take this, distribute that, and that's going to give us a, I'll put it over here, a negative 2a and a negative 2h. So just distributing that, and then we have a 7. So now we look to see if we have any like terms. And as I look here, I don't see any like terms. So this then becomes that. I wanted to show you how it's done. It's a little tedious. Now what they're asking for here, in this next one, they're saying x is this. So we have this value minus this value. So we put in our first equation all of this, which is what we had up here, and we're going to actually end up with that, which is what I have down here already, and then minus this over here, which is our minus a. So we put a in there like we did over here, but there's a negative sign now outside the parenthesis. So what does this become? Well, I squared this term, which gave me this, minus this, that, got rid of the parentheses here. Then when there's a negative in front of a parenthesis, you take away the parenthesis and just change the signs. This became a negative, this became a positive, that became a negative. Then I grouped like terms. Now notice my a squares cancel out. My plus 7 and a negative 7, that subtracts out. My positive 2a and a negative 2a cancel out. So what am I left with? Well, I'm left with a 2AH, which I have here, H squared, which I have here, and then a negative 2H. And that's all for this one. Again, it's tedious, I know, and it's just got to go slow, check your signs. Now for this next one, it's all of this, which I know is this, which I put here, and they're asking us to divide it by H. Now, in order to divide this by H, I see I have an H in here, an H in there, and an H in this term. I could factor out the H, which is what I've done here. And then now I can just cancel them out. So my final answer for this one is this right there. Now, I use the technique of writing some of this out ahead of time because it just gets so tedious to do it item by item. But as you do a problem, you're going to have to write it out too. I wanted you to see how this function notation fits into evaluating something that's like this. And again, this is on page 51 and, well, 51 basically in your textbook. As we go on to the last example, we're going to talk about applications again. These are sort of like word problems. And some of the words we've used already was break even. That is when you had two equations and you're looking for a point where your revenue and cost intersect. That's your break-even point. And then we talk about profit and loss. We'll go over that in a moment. Fixed cost. Well, a fixed cost would be a building. It will be a machine. It will be those two things, the building and the machine. Those are the fixed costs. Variable costs will be the amount of electricity, the number of employees that you have, the number of loose materials that you're going to use to produce something. Those are variable costs. Price and demand. We know if something is too expensive, people aren't going to buy it. So there has to be a point where the price is such that you get the demand for your product. Again, this is a little bit of economics that I'm not an expert in, but give you an idea what these words are. And then mathematically, we can say that if your revenue is less than your cost, you have a loss. If your revenue equals your cost, that's what we have here, at this point, you break even. And then if your revenue, that is the money from selling the product, is greater than your cost, you have a profit. And then you usually have stockholders, and depending how your business is set up. Years ago, I was a president of a junior achievement company where we made things and sold them, and we found out a lot about this. So maybe some of you have been that too. Now, in example 7, as we look at the textbook, there are a lot of tables, a lot of graphs, and what I'm going to do is kind of give you a brief summary of what's here. It would be just too much to put on the board all of the stuff that's in the textbook. But here we're talking about the price, demand, and the sale of cameras. This one manufacturing outfit had found that if they have a certain price on their camera, they would sell so many. But if they lowered the price, they would sell more. So that gave rise to table 4. And they're asking you to complete table 5 using this regression formula. And again, we got the regression formula by plotting a scatter chart and then making a line to indicate the average of what this would be. So as we see the increase in number of cameras, the price of the camera goes down. And that's a very typical thing. I know when flat screen TVs came out, I got a 28-inch for $1,100. Now a 28-inch is what, $300. So it just goes to show you. This does tie into real life. So that's basically what they're illustrating in this particular graph. And you would plug in the number of cameras you want to sell. Remember, this is your X, and that would give you what the cost might be using this formula here. Okay, to wrap up this section, the earlier example was price. Now, when they actually did the analysis of cost, they didn't get a straight line, but they got a curved line. And this indicates that as your costs increase, the number of cameras that you produce, and these are millions of cameras, that there is a period of time that your costs go down again as you produce more cameras. Your costs will increase steadily and then peak and then drop down. So again, the production of lots of cameras and keeping the price low seems to be a very good recipe for selling things. And again, all this is in the book, and you will be getting to do some examples on the QuizMes. And there are, again, plenty of examples in the book, but these are available to you through your practice, QuizMes, and then later the test. Okay, again, bring any questions that you might have into Math Zone. We're happy to help, and we hope this is a help as well.